are both the largest value, then the MID of the sequence would return 1 and 3. These are some examples that I have presented. Suppose my sequence is 25341. So applying an MID on this sequence would return 2 because the second element, which is A2, is my maximum element in the series. Similarly, when we have another sequence Bn, which is j square, where j goes from 1 to n. So it's basically like the squares of the first n natural numbers. So since it's an increasing function, obviously the last element, which is n squared, would be the largest. So putting an MID on Bn would return n because B of n, which is the nth term, is the largest term, which is n squared. So we get an idea of this. Now, in proper mathematical field, there's nothing particularly attributed, no name particularly attributed to these kind of functions. But since this entire paper is me working on these stuff, especially in binomial families, so I'll just give them this MID name. And it's kind of nice because you guys might have seen this a lot in elementary programming, because often we have to take out the index of the largest element in a list. So when we are dealing with Python or C++, if you have done. So I'm trying to bring that into the mathematical sense, but we'll just do a case study of a binomial sequence. Consider this normal binomial sequence with no emphasis on the word normal. It just means that it's the general one we see often. So NCR, n is fixed, and R varies from 0 to 1. So we can actually plot the binomial distribution, or the binomial coefficients. And the point is that even though it's defined on discrete numbers like r equals 0 to n, we can generally extend the binomials to something called the beta functions. And beta functions are continuous. So this is just plotted just to make a good visual representation of what binomials would look if they were defined on the reals. And you know that beta functions are basically some ratios of gamma functions, which are basically factorials of real numbers. So as you can see, that binomial, actually the normal binomial coefficient is a unimodal graph, which means that it has only one peak. And there are small local maximas and minimas near these corners, below -1, above 4, but we don't really bother about them. We bother about the support, which is from r equals 0 to n. And you can see that from r equals 0 to n, this thing is actually, and n would be 3 in my case, because I have given 3 cx. So it's 1 at 0, it should be 1 at 3 as well, and it's unimodal. So we can see that generally what do? We see which is the maximum term when we are doing a binomial expansion. So you can see that the mode here is not an integer. It's actually 1.5 exactly, which is pretty interesting. But then again, it's like a symmetric graph. So you know that NCR is NCN minus R. Same holds for beta functions as well. And so the mode is exactly at 1.5. So it's not on an integer. But like if we didn't have any reals, then 1 and 2 would both be the points at which the binomial is maximized. What you can do after this binomial is you can put a weight on this binomial. By weight, I mean some number to the power n minus r, where k is a natural number. And then try to see the binomial again. And for these weighted binomial sequences, what happens is that the graph is no longer symmetric because you have a weight which is asymmetric in n and r. So technically what happens is that if you go back to this, you can see that 1, 1.5, and 2 are for 3cx. Now I plot 3cx, but with a weight of 2 to the 3 minus x. And you can see that 1, 2, and 1.5, these are no longer around the mode. So the mode becomes 0.819, it's left shifted. And you can clearly see that because as r goes to 0, we have a k to the n term, which means that this thing basically rises from 1 the more we increase the value of k. But at the same time, you can see that, it's not exactly at 0, at r equals 0, that the maximum value is attained. It's attained somewhere in between, but definitely not at the point where without a weight we would attain. So basically, if you keep on increasing the weights, you can expect that this will like left shift until it basically becomes 0. Now consider this sequence NCR 0 less than equals r less than equals. So this might be a high school result that we all have probably proved, that when r equals r equals n by 2 when n is even. What is r? R is basically the index at which, the value of r at which NCR is maximized. We know that when n is even, it's just n by 2 because there are odd number of terms here. and the middle term is n by 2. And when n is odd, then there are even number of terms. So there are two middle terms, which are n minus 1 over 2 and n plus 1 over 2. At these two terms, the graph is maximized. So clearly, if I just go back one last time to this graph, we could see that in this case, 3 is odd. So 3 plus 1 over 2 is 2, and 3 minus 1 over 2 is 1. So at these 2 points, the binomial was maximized. So a general MID function on normal binomial coefficients would be such that fn equals n by 2 if n is even, and fn equals n minus 1 over 2, comma n plus 1 over 2 for all. Now you see a very basic problem in this, is that sometimes for some n, this MID would return two values. And you can't have a function that takes one input and returns two values, because like one many functions don't exist. So we have to like deal with them somehow. And one of the nice ways to deal with these is by using sets. So how do we actually use sets? I'll just come to the definition, but you know that a set can contain multiple elements. So instead of defining a function from a set to the other set, like we generally do, if you define it on a set of sets to a set of sets, then you can basically take a set of some numbers and get it to some other number. In particular, if you take, instead of taking the f of n, if you take f of the set of n and then put it to the set of n minus 1 over 2, comma n plus 1 over 2. So as long these two things are distinct, you will have a well-defined function. And we'll just do a domain equals codomain when we set the function, because as I talked previously, we want to compose these functions later to see some nice properties. So consider fk is the maximum index determiner of the sequence, which is the weighted binomial with k as my weight. So I define the function fk from the power set of naturals to the power set of naturals with some rules. So firstly, we don't know where the empty set should go, so we just send it to 5, because we aren't really bothered about empty sets in this case. The next one is what it does to singletons. So if we have a singleton n, it sends this to these two numbers. So these are the things which we need to be a bit careful about. So this is the floor function of n over k plus 1, and this is the floor function of n plus 1 over k plus 1. So floor function, if you are aware, it's just like box of x as we know as it. So like it's the greatest integer that is less than or equal to the number. So like if there's 2.5, then a box of that would yield 2. If it's 2, it will yield 2. And if it's like minus 2.5, it will yield 3, minus 3, because minus 3 is like smaller than minus 2, and also is the greatest integer which is smaller than minus 2. So you just go leftwards. So that's the point. And this is my function. And why does this function generally maximize this? We'll come to the proof shortly. And since we are going from the power set of n to the power set of n, it's generally a question what would happen if there are a lot of elements instead of a singleton. So since we are only bothered about singletons, we have a meaningful formula for, say, f of set n. So what we do is we just take these numbers and break them, partition them into singletons. So why can we do that is because any set can be partitioned into singleton sets as long as all the elements are distinct. And they have to be distinct because that's the definition of the set. So a1, a2 up to an. So that would be the union of f acting on each of the singletons aj, j equals 1. Now for the MID, it's easy to verify for k equals 1, as we just showed that how if n is even, then we have n by 2, and if n is odd, then we have n plus 1 over 2 and n minus 1 over 2 as the maximum indices. So generally, we want to find a value of r such that my term r minus 1 less than equals term r greater than term r plus 1, where term of r is given like this. So you can see that there's a different nomenclature rather than what is given in generally. So t0 would be nc0 k to the n minus 0, which is the first term. So instead of writing t1, I'm just writing tr. So basically t0 would mean the first term. It's just for convenience because you get r here, you get r here. So it's nice. So basically we need something like this. Why is it less than equal to? It's because you can have some cases where two different indices are the same. So I haven't explicitly proved why three different indices cannot be the same, but it's like along the same argument. So once you get this proof, you get all the other proofs. How do we prove these? We generally take the r minus 1th term, r plus 1th term in this nomenclature. And this gives us the relations n plus 1 over k plus 1 minus 1 is less than r, which is less than equals n plus 1 over r plus 1. Sorry, there's a typo. This should be k plus 1. I don't think I have a highlighter here, but this should be k plus 1, because otherwise this won't make sense. So yeah, so if n plus 1 over k plus 1 is an integer, then we are done, because then you know that r is equal to n plus 1 over k plus 1. And then both r and r minus 1 are solutions because both of these are clearly integers. At the same time, you could also see that like this thing holds. You can actually put those terms in here. So ncr minus 1 times kn minus r and nc kn minus r plus 1 and ncr kn minus r. If you like cut out everything and put n plus 1 by r k plus 1 as some integer, then you can see that both r and r minus 1 are solutions. Otherwise, see, if this is not an integer, r has to be an integer. So r has to be the greatest integer function of the floor function of n plus 1 over k plus 1. So which is the integer just left of r. Clearly, fk definitely makes sense now, because so this is the value where r is maximized, and you can clearly see that r minus 1 is no longer a solution in that case, because like r minus 1, if you put it down, it's too small. But if this is an integer, then r minus 1 is an integer, which is basically n plus 1 by k plus 1 minus 1. This is also an integer. So in that case, both of the terms are same. Okay. So what does this actually mean? So I just showed you a proof, but there was no clear way of understanding what this means. So this means that you have k, so you have k plus 1, because in the function, you have the denominator k plus 1 over here. So basically, we want to look at the ratio n over k plus 1 and try to find out that what quotients and what remainders actually give what values. So suppose n by k plus 1 has a quotient q, and the remainder is from 0 to k minus 1. So it can take any value from 0, 1, 2, 3 to k minus 1. Then we have the MID of this set n. And what is this set n? It's basically the binomial sequence NCR, where n is fixed. So fk of this set n would be q. And what is q? Q is just the quotient when n is divided by k plus 1. And we see that when n over k plus 1 has a quotient q, but the remainder is k, like not 0 to k minus 1, but k, which is ironically like k plus 1 minus 1. So it's just before k plus 1, and is also the maximum possible remainder. So when it has the maximum possible remainder k, then fk of n would be q and q plus 1. So in that case, you can see that n plus 1 over k plus 1 has to be an integer, and so both q and q plus 1 are your values. So what are some examples of these? Let's just consider n to be 30 and the weight k to be 6. So we have this binomial sequence 30 CR, 6 to the 30 minus r. And you can clearly see that what is k here? It's k is 6 and 30 is n. So we want to divide n by k plus 1, which is 7. So we divide 30 by 6 plus 1, and we see the quotient is 4 and the remainder is 2. Now the remainder is in this range. So what's the quotient? What's the value? K plus 1 is 7. So the remainder is not 6. It's less than 6. So we only have one maximum index, and what is that? It's q. So q is 4. In this case, we are taking n equals 27 and k equals 60 once again. And now we see that when we divide 27 by 6 plus 1, we get 6 plus 1 to 3 plus 7 minus 1. So this is 7, and this is 7 minus 1, which is 6. So it's basically the case where the remainder is k. So since it's k, what's the quotient? The quotient is 3. So 3 comma 3 plus 1, which is 3 comma 4, both would be the maximum indices. So if you like go in and check putting these values 27C3, 27C4, and 6 to the whatever weight we have, you will not only see that these are equal to each other, but you'll also see that these are greater than any other values present here. And just like that, the argument, as I already said, is very easy to understand. Okay. So now that we have completely characterized what fk is, it's just box of n by k plus 1 and box of n plus 1 over k plus 1. You'll want to compose f. So why do you want to compose f, and what are the properties of f first? So first we said fk is not 1, 1. And it's clear. So how do you actually see that it's not 1, 1? Let me go back and try to take some examples. Okay, let's just go to this slide. This slide is good enough. Suppose n over k plus 1 has a quotient q and a remainder 0. Then what is your output? It's q. When n over k plus 1 has quotient q and remainder 1, your output is again q. So if you take fk of n, and if you even take something like n plus 1, you'll get the same output q and q. So basically, you can have two different values of your singleton set, which would give you the same quotient. and therefore it's not one. And it's also onto, so it's surjective. And how is it surjective? It's surjective because of the very easy thing that given any value of q, you can always generate more than one value of n. So like this step is not difficult. Obviously, it's not one, so there's no unique preimage, but there can be a lot of preimage. You can always like multiply it with k plus one, add one remainder, and that could be a value of n. So it's surjective. So if it's not one and it's surjective, then yeah, like it's not invertible. So we can't do anything related to the inversion of this function. But the one thing that we did was we made the domain and the codomain same, which means we can compose these functions. We can't go in the opposite direction, but we can definitely go in one direction. So why compose fk with itself? Okay, before that, there's a small thing mentioned here that even 0 has a preimage. Like if you say n equals 2 and k equals 3, then you would see that n by k plus 1 and n plus 1 by k plus 1 basically yield a 0. Also a 1, but both 0 and 1. So you could very well see that like 0 can have a preimage, which is n equals 2 under k equals 3. Okay, so why compose fk with itself? So we have seen that terms in fk of n, what are they? They are like n by something box. But whenever we are doing n by something, it's yielding a number which is less than n. So if you are composing fk with itself, so you just go dividing it by k plus 1, k plus 1, k plus 1, k plus 1, like of the order of k plus 1. And basically, at some point, you are like way too small. So you're taking box functions, right? So if you are not taking box functions, then it would just go on because you're dividing and it would go on till infinity. But since you're taking box functions, like what as soon as like fk compose say t times of n goes below 1, the box of that would be 0. So technically, if you're taking like box functions and dividing, you're taking box functions and dividing, as soon as it will go less than 1, it will go to 0. And you can kind of understand how quickly it will go to 1 because you're dividing by something of the order of k plus 1. So you know that after some logarithm steps or logarithm time, it will go to 0. So it's basically a kind of log decay in this thing. Also, we are trying to see that starting from a single element n, how large can be fk compose t times with itself on this n. So why does this question even arise? Because we saw that sometimes n can go to only one quotient q, but sometimes n can go to quotients q and q plus 1. And when you apply the f again over q and q plus 1, you know by partitioning, it's f on q union f of q plus 1. So technically, there are chances that q diverges into 2 more, q plus 1 diverges into 2 more. So technically, we don't know a priori how many terms there might be in this fk compose t times over n. So it might be very large. Maybe it's unbounded if like the more and more n you take. Maybe it's a function of n, or maybe it's not. So these are the questions that we are interested in and we want to answer. So we want to prove that there are actually a bounded or finite number of elements. Whatever value of n you take, you only get a finite number of elements. So for that, we take suppose that j and j plus s, these are two random numbers, are present in this fk compose t times on n, where s is greater than equals to. And why do I say greater than equals to? Because, well, in j and j plus 1 were in the set, then it's kind of obvious. You already saw q and q plus 1 were in the set. So j and j plus 1 can definitely be in the set. And so I'm considering that j and j plus s, where s is greater than equals 2. Before I proceed. Okay. So yeah. So j and j plus s, suppose s is greater than equal to 2, are present in this set. Now, if you think carefully, I told you that one j can have a lot of preimages. And what are those preimages? Those preimages are precisely k plus 1 times j minus 1 all the way up to k plus 1 times j plus k. And you can clearly see, like, if you divide these by k plus 1, you see that the remainders are like from minus 1 to k. And you can definitely find out from the definition of the functions fk of n that these are the preimages. So no other numbers other than these numbers can yield you a j under the action of fk only one time. So fk on either this or this or this or this or correction of this can yield you j. Now j plus, this should be s, I guess this type again. So j plus s can come from the application of fk on these numbers. So these numbers are basically, instead of writing j here, I'm writing j plus s and expanding this. So these are the numbers. So now this is the smallest number from where j plus s can come, and this is the largest number from where j can come. So let me take the difference of those two and see that whether those are greater than s or less than s or what. And you can see that the oscillation is basically like the largest element minus the smallest element. So under this condition that j and j plus s are probably the largest elements there, the oscillation under this condition would be this element, which is the smallest element from where j plus s comes, and minus this element, which is the largest element from which j comes. And if you subtract these two, you can get s minus 1 times k plus 1. So this is greater than or equal to 2. In fact, you could also show that in particular, like k is always greater than or equal to 1. So we are not considering the value when k is equal to 0, because that would just make the entire binomial sequence trivially 0. So the smallest value that k can take is 1. So this 2 into s minus 1 is greater than or equals 2. But if you see that if you put k equals 1 here and you cut off the 2's here, so s is greater than or equal to 1. But that is like almost trivial. You already have proof that s is greater than or equal to 2. So basically, instead of this entire thing, you could actually say that s minus 1 times k plus 1 is actually greater than or equal to s. And how could you do that? Because even if you consider the smallest value, 2s minus 2, 2s minus 2 is greater than or equal to s, which means that s is greater than or equals 2, but which is what I considered. So in particular, we have a stronger bound. We not only have a bound that this term, like the oscillation of fkt minus 1 composition is greater than or equal to 2, we can also say it's greater than or equal to s, which was our oscillation of fk composed t times. So basically, you see that if something which is greater than or equal to 2 exists in fk composed t times, then if we trace back our path, so instead of going further composition, if we like trace back to what could be the pre-image, we could see that the pre-image has to have at least an oscillation which would be greater than s. And now if we trace back one path again, we'd see that the oscillation of fk composed t minus 2 times would increase further and further and further. So this is clearly increasing. Either it increases or it stays at like s because it's greater than or equal to. So what does that mean? That means that this oscillation is either increasing or it's staying constant. But now if we trace back all the way up to like fk1 and fk0, you would get n, but n is a singleton. We have seen that if j and j plus s remains, then the oscillation of every single fk t's, where t is less than this t here, would have an oscillation of greater than or equal to s. But that is not possible because our first element that we started from was a singleton. So it has an oscillation of 0 because the largest element is the same as the smallest element. So this is wrong, clearly wrong. So therefore, the at most oscillation that fkt composed t times can have is 1, which means that at most a value j comma j plus 1 can be in a sufficient number of compositions of n. And you know that this is possible because of the definition, like q comma q plus 1 is present in some of the values. So therefore, we get something very interesting. We get that even if you apply this fk many times, like a large number of times on a singleton set, at most you would end up with 2 consecutive numbers and no more. So therefore, there is no increasing things, there's no unboundedness, there's nothing like that. So we are kind of relieved that it doesn't blow up or do anything like that. It's just 2 elements at most, and those 2 elements have to be consecutive. So now that we have discussed about what the girth or the oscillation of these fk composed t times would be, let's try to think about how fast these things would go to 0. So we have a crude idea like n divided by k plus 1 to the t. If it's less than 1, then t would be something like log of n over k plus 1. Right. So, but we do it in a more deterministic sense because we want to be deterministic in this problem. So there are 2 ways to do this. So as you just saw that j and j plus 1 or q and q plus 1 can be n. Suppose q is 0 after a large number of compositions, but q plus 1 is 1. So there are actually 2 ways to fix. One way to fix is when there is 0 in the kth iteration of f, but there is no 0 in the k minus 1th iteration. So what does that mean? For example, you were taking the MID of say 2, and under the weight k equals 2, the MID of 2 goes to 0, 1. So there is 0 in fk of n, but there is no 0 in fk minus 1 of n, which is 2, but this is 0, 1. And this is called individual fixation. So like any one term in your output has to be 0. So that would mean that there's an individual fixation. What does that actually mean? It means that if you were to take a path, like from n, you have many different paths to go down. So whenever you have q and q plus 1, one path goes through q and one path goes through q plus 1. So individual fixation basically says what is your shortest path. Your shortest path is such that it goes to 0 first. While universal fixation means that your fk minus 1 of n is not equal to 0. It's just not that it doesn't contain 0. It's not equal to 0. But f iterated k times on n is equal to 0. Which means that every single path that you take, either through q or through q plus 1, you branch off at any different point, all of them has to go to 0 after these many iterations. So that is my universal fixation, and individual is like the shortest path, which is the fastest one that goes to 0. Other terms can be greater than 0, like technically 1, but which is the fastest. So these basically give a very deterministic rate at which n falls to 0 under fk, and you'll see that they have very nice properties associated with them. So generally, we consider a case study here. So I'll just talk about when k equals 2, that is k plus 1 equals 3. And why will I do that? I'll do that because just for convenience. So you can do the same when you are working with higher values of k. And I'll also represent f of k plus 1 instead of representing f of k, because it just makes things easier. So obviously there are some notational issues here. You can definitely make these notational issues better. You can define very strict notation, which you have to follow everywhere. But these don't really matter. This just means that the value of k plus 1 is 3. And I define two sets. So what is this set? Phi of 3 under a parameter t is all those values, is all those natural numbers, which such that 0 belongs to f3t of n, and 0 doesn't belong to f3t minus 1 of n. But what is it? This is the individual fixation exactly. So basically, phi t3 is under this weight k plus 1 equals 3, all those numbers which are individually fixed in exactly t steps. Not any more, not any less. So, and phi t3 prime, this is exactly the natural numbers, set of natural numbers which are universally fixed in exactly t steps. So we would want to see that given a number of steps, which natural numbers are individually fixed in that number and which natural numbers are universally fixed. So how do we go along with this? One very nice way is to look at the same thing, what values something can come from. So there's a very nice diagram which says that k can come from 3k minus 1, 3k, and 3k plus 1, and also 3k plus 2. So just like I showed in the proof when we were proving that no more than 2 consecutive elements can be present in fk of n or fkt of n, it's the same thing. But in the case where the value of k plus 1 is 3. So if we have a small value k plus 1, please don't confuse this with k. We are considering k to be 3 here, k plus 1 to be 3 here. So you can come from 3k minus 1, 3k, 3k plus 1, and 3k plus 2. And you know that universal fixation means that every path has to be fixed, which means that the smallest path and the largest path has to be fixed. While individual fixation means that any one can be fixed. So this means that these three numbers correspond to your individual fixation. Why? Because 3k plus 2, not only does it take you to k, it also takes you to k plus 1. If you just do the general divisibility property, you'll see that it also takes you to k plus 1. So if you're considering k comes from these three numbers, you are basically only trying to fix the fastest path. You're not fixing this path because this path can go to k plus 1, which is not necessarily 0 if k is 0. It's 1 basically if k is 0. But when you're tackling universal fixation, you have to tackle this path. And what does 3k minus 1 take you to? Basically, 3k minus 1 takes you to two different numbers, k minus 1 and k. And k minus 1 is always smaller than k. So k is the larger path of the two. So basically, you are fixing the larger path here, while an individual, you're fixing a smaller path. So basically, that is the difference. So when you have k, you would have 3k minus 1, 3k, 3k plus 1 as the previous layer from where k can come from under universal fixation. Well, from under individual fixation, k can come from 3k, 3k plus 1 and 3k plus 2. And you can clearly see if k comes from these three and these three come from three more, say for an example, you can get a very nice bottom-up tree structure. And this tree structure is very nicely seen here. So instead of doing a bottom-up, I have done a top-bottom here. So it's more or less like a pyramid structure in this case. But it's really nice. you can see that under this fixation, the universal fixation scheme, so 0 has to come from 1. 0 cannot come from 2 because 2 gives rise to both 0 and 1. So 0 cannot come from 2 under universal fixation. 0 has to come from 1. 1 comes from 2, 3, 4, but not 5 because 5 also gives rise to 1 and 2. So 5 cannot universally fix 1. 5 has to only individually fix 1. So 0 comes from 1, 1 comes from 2, 3, 4. 2 will come from 5, 6, 7, 3 will come from like 6, 7, 8, and so on. So you get all this bunch of large numbers that you get. And basically, 3 would come from, if it's k plus 1 is 3, it basically would come from 8, 9, 10. 4 would come from 11, 12, 13, and so on. So basically, these are also like disjoint. So 2 comes from 5, 6, 7, 3 comes from 8, 9, 10, and so on. And then you can do it for 5, 6, 7, 8, 9. You can clearly see that since these are disjoint, so then for every single element, there'll be 3 elements in the bottom and the lower layer. And those are disjoint. So therefore, if there are L elements in this layer, there are 3 L elements in this layer. And that is what I have written here. So basically, if it's 1 here and 1 here, it's 3, then it's 9, then it's 27, then it's like 27 to 3 is 81, then it's 243, and so on. Under individual fixation, though, this does not hold remotely like that. Under individual fixation, you see that there's 0. 0 can come from 1 and 2. 1 can come from 3, 4, 5. And 2 can come from 6, 7, 8. You have already seen that this is under individual fixation. So individual fixation had these things: 3k, 3k plus 1, 3k plus 2. So 3k, 3k plus 1 with 3 into 2 is 6, 3 into 2 plus 1 is 7, 3 into 2 plus 2 is 8. So here is the layer just below 1 and 2. Similarly, here is the layer just below this. And you can see that after some certain point, after this layer is gone, you still have this disjoint set. Like 1 comes from these 3 and 2 comes from these 3. So for every element, you still have 3 elements and 3 elements. So basically, if you have L elements in this layer, then you have 3 L elements in this layer. The only difference is that in individual fixation, the very first layer, like this is the 0th layer, say, and this is the first layer. The first layer has 2 elements, while in universal fixation, the first layer has 1 element. And the rest are all just like multiplying with 3, 3, 3, 3, and so on. So you can basically exactly find out, you can do some pattern observation on these trees given here. And if you try to observe those patterns and also analytically try to solve them, then you will see that this thing, so let me just go back and try to like confirm what these are. You see that phi 3 prime, this is universal fixation, while phi 3 t without a prime is just individual fixation. When you go back here, you see that phi 3 prime, which was my universal fixation, is going on like this. And phi 3k is just going on like this. Note that phi 3t is 2 phi 3 prime t. You can clearly see if you try to take a difference. What's the cardinality of this element? And what's the cardinality of this element? So you can see that twice as many get fixed in k steps under individual fixation as compared to universal fixation. That is pretty interesting, because if you have a universal fixation here, you could see that under t steps, if these numbers get universally fixed, these number of numbers, then twice that number gets fixed in individual fixation. This is very interesting. This means that, what does this mean? What does this mean as we like generalize k? Does it mean it stays twice? Because if it's twice, it means a very large number. Like if you have 5 elements being fixed here, it's 10 elements being fixed here. But in all probability, it doesn't really seem like there should be so many numbers in for general k, because it's just the 2 paths. The 2 paths are like one is going through q, one is going through q plus 1. So what is the actual value which is getting fixed? So generally, using the same arguments, using the same tree structure or pyramid structure which I showed, you can also do the same for general k as the weight, and you'll find these equations over here. Okay, this is just a bracket. It's not a box function. It's just a bracket over here. It's an integer. So these are your 2 different universal and individual fixations. And you could clearly see here that phi kt, the cardinality of that will be k over k minus 1 times this. And obviously here k is not the weight particularly, but it's k plus 1 in particular. I mean, it's just this thing here. So it's kind of nice to see that it's k by k plus 1. Clearly you could see that for in general, when k was 2, like not k plus 1, but when the weight was 2, it was 2 by 2 minus 1, which was just 2. So in general case, when you have say like your weight to be 10 or something, it's just 10 by 9. So now you can see it's not that big of a difference. 10 by 9 times something, it's fine. It's not like doubling things out. But when it's 3, when k plus 1 is 3, then this is 2. So it's really something that you should keep into mind, that when it's very small, then things actually get doubled or something. But when you go large, like you see, as you take the limit k tends to infinity, this basically become the same. The cardinality is always the same. These are just two very interesting properties that you can see. And basically, this is mostly what you had to do when you take up this problem, because you want we couldn't invert the function, we couldn't do any other techniques on that. We could find out all the solutions. It was completely deterministic and also easy to find out. So what I tried to do is I tried to find out that how fast things go and how quickly things converge to zero. And that led me to finding out what universal and individual fixations were and how they were related to each other. And now you can kind of, in the future, what you can try doing is try to make an algorithm maybe that takes a probabilistic, maybe each time your fk of some n bifurcates into q and q plus 1, it does a coin toss. And based on what toss it does, it goes to either q or q plus 1. So at every step where it gets a bifurcation, it does a coin toss and decides on where to go. And on a large number of iterations, you could probably see that which one of these things can go to zero in the quickest number of steps. So it's not that easy to find out, because like you can have a lot of bifurcations. They don't happen at, and it try to figure out that whether there are like two different times, like one for individual and one for universal, or are there intermediate times, like say one goes to zero in 10 steps, one goes to zero in 13 steps, whether there are something that goes to zero in 11 or 12 steps. And you'll see that there are nothing in between. So universal fixation and individual fixations are basically consecutive steps of each other. But it's a nice project that someone can try to do. Okay, so that we have completed with the more stronger part of what we are discussing. Let's just go behind the motivation of this problem, because without explaining the motivation, this just seems like it's very random. It just comes out of nowhere. And after the motivation, I'll also talk about something that I cannot resolve, and something that if I can resolve or any of you can resolve, it could be very interesting. So first, let us forget that it's a function and there's this plot f. So as we get value of n, it increases. We just plot the values of f of n. And instead of writing it as a set, we just plot the different values. So this is just for the case where k equals 3. I'm still continuing the case study here, just interesting. And you can see it's a staircase function. It's a really nice thing. And I often call it a falling function because it basically falls through the values of n as you compose it. But you can call it an MID. It's not a big deal. This was an old image, really. But yeah, so this is a nice staircase function. And where else can you bring this staircase in? So let's try talking about something very nice. Let's talk about this matrix. And this is a lower triangular matrix. All the elements here are zeros. And I just didn't write anything there just to make it look neat. So what is this? If we try to, like, in our heads reposition this thing, like we have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Like if we just center align this entire thing pulling down, then we see it's just the Pascal's triangle. Like Pascal's triangle has 1, 1, 1, 1, 2, 1, and so on. Or the binomial coefficients, if you would know. And you can see that we are trying to go somewhere using this. And what we are doing is that we are taking another matrix here called H5, which is 1, 2, 1, 4, 4, 1, 8, 12, 6, 1, 16, 32, 12, 24, 8. So what exactly is this matrix? It's clearly not understandable just by looking at it. But just through a bit of algebraic manipulation, you can clearly see that H5 is L5 squared. In general, Hn would be Ln squared. So this is the square of the Pascal's matrix. So this is called the Pascal's matrix because it's just the lower diagonal Pascal's triangle. And as Ln I comma j is ICJ, where I is greater than or equal to j, but the nomenclature is the same, like the first element is 0, 0. And 0 when I greater than or equals j, and when I less than j is 0, I greater than or equals j is ICJ. So what is Hn? Hn, let's try doing the multiplication. It's Ln I comma k comma j. So basically ICK kcj, and if you took the sum, I think it's a well-known result that the sum of ICK times kcj is 2 to the I minus j ICJ. Like it's a pretty well-known result. You can even try doing it by breaking out the factorials and taking something out, and you'll be left with stuff like this. So therefore, H and Ij is Pij, and what is Pij in our case? It's just the binomial family with n equals I and r equals j. So which is exactly our binomial sequence with weight k equals 2. And you can clearly see, or maybe not clearly, but you can have a gut feeling that as we try taking the higher powers, ln3, ln4, we can basically go to the k values of 3, 4. Like here, instead of 2, maybe 3, 4, 5, 6, and so on. As we take like ln cubed, ln4 power, and so on. And now if you embolden or maybe color those values that are maximum in each of these rows, like in the row of 1, 1 is maximum. In row of 2, 2 is maximum, not 1. In this row, 4 and 4 are maximum, and so on. We can actually replicate this staircase sequence very nicely. You clearly see that this falls like a staircase, and this actually continues. You can completely prove because these are basically some of the binomial families for constant n. Like in this case, n is what? 5, n is 4, n is 3, n is 2, n is 1, n is 0, and so on. So these are basically the connections that you can have with the Pascal's matrix and what problem we are doing is the maximum index determiner of the binomial family. And basically that's everything that the motivation is. There's also something very nice regarding this, which is not generally useful in the general k term, but for k equals 3 term. So that is why I did the case study of k equals 3 term, because that was my initial motivation when I first started the problem many years ago. So it's basically something to do with generalization of cubic family. So we know that like squares and cubes are like the 2D renditions, 2D and 3D renditions of the cubic family. And in 4 dimensions, you have the tesseract, and 5 dimensions, you have the pentaract. So I won't go deep into them because that would need a different separate discussion altogether. But basically, if you have the cubic family exactly has these matrix as the number of, say, faces. So for example, this is a square because it's dimension 2. So the square has 4 edges, 4 vertices, 4 edges, and 1 face. And this is n equals 3, so it's a cube. So a cube has 8 vertices, 12 edges, and 6 faces. So it's just like that. It's a generalization of cubic family. It's very nice. Okay, coming to the very end of my lecture, I'll just talk about a bit of a problem that I couldn't solve. And what I was trying to do all this time, I was looking at a binomial family and I was trying to find out the MID of that family. Now, like I want to generalize the MID of that family and trace back that. Okay, binomials are maximized by these MIDs. So what if we generalize MIDs? What curves or what kind of binomials do these MIDs maximize? So what I did was instead of n by k plus 1, n plus 1 over k plus 1, I just added n plus 2 over k plus 1. And under this ad hoc generalization, what sequence could this function be an MID of? And this is a problem that I still can't resolve because it's sheerly difficult to me. And why is it difficult? Because of this very nice property. So you could see that there's no way to say what is an MID of, but let's see what this asymmetric unimodal curve gamma x, which is an MID of, what properties does it follow? So if say x equals x naught is the mode, so it's the unimodal, so there's only one mode. Say x equals x naught is the mode under the general real case. So it would be such that x naught lies between q and q plus 1, such that gamma q is greater than gamma q plus 1 if n by k plus 1 has quotient q and remainder r, where 0 less than equals r less than equals k minus 2 in this case, not k minus 1, because I added one extra term. So therefore, for all these, the gamma of q would be greater than gamma of q plus 1. So basically, if you think of it like if there are like two different integers and the mode is in between, so the left value would always be greater than the right value. So this would be like more sloping in this direction and higher in this direction. However, for r belongs to k minus 1 and k, so there are two different values. So if n is divided by k plus 1 is q plus r, where r can be k minus 1 or k, then the mode will still be in between these two numbers, but gamma q has to be equal to gamma q plus 1. So like for two different values of k, we would have such that this point and this point would be the same, irrespective of what the nature of the graph is in between the 2 points. And why is this difficult to understand? Because binomials are generally finite support functions. Like it's from 0 to n. So generally as n increases, your support also increases because it's 0 to n. So if n increases 0 to n plus 1, the support is increasing. And so basically, so does your MID. Because basically, if you just keep k to be your constant and increase n, it will get stretched out. So it will become more and more right shifted, and MID should increase. So technically, if your remainder increases, basically if this number k plus 1 q plus k minus 1 goes to k plus 1 q plus k, we expect a right shift in the maximum. However, we still have to solve this condition gamma q equals gamma q plus 1, which means that despite a shift in the entire graph and the shift in the maxima, they have to have the same value on the two different integers q and q plus 1, which means that it just can't be a nice shift. There has to be a shift in the skewness of the curve. Because say if this was like this, then the next function which is right shifted has to have like a steeper slope down instead of a gentler slope. And this can be visually seen in these two different things. I can clearly see that this function has a greater support, like it's a larger support than this function. Obviously, these two are not curves that I have found out. These are two very different curves optimized to hold the same value. So the problem is still an open problem. But yeah, like these two are two things such that these are different support. Like this has a larger support than this. Also, the maximas are different. Like this has a maxima here and this has a maxima around here, a bit right shifted. So in both the cases, the value is taking the same. The value is the same at 1 and 2, but the maximas are different and the supports are different. So we need to find a curve like this so that even if your n shifts, your values at these points stay same. And you can clearly see that the skewness of this curve is changing. So, like from probability theory, there is something called the skewness and the kurtosis of a curve, which says its peakedness and how skewed it is. So basically, your third moment and your fourth moment, in particular, your skewness and your kurtosis of the curve, needs to change. So that just makes things very non-trivial in nature. So, like, if any of you can have any ideas or found out the problem, you can definitely like write to me at my email here. If any of you want me to share you these slides, you can also write to me. I am active on this email. I'll just respond to you as soon as I am free. And definitely, if someone has any ideas, like I have been bickering on this for quite a while now, and I would definitely appreciate an answer from anyone. So, having said that, I think we are already done for an hour. I would like to stop my presentation. And yeah, I'll stop sharing my slides as well unless someone wants to ask some question. And Moitra, you can continue, I guess. Sure. No, no, let's just be clear. Like this formulation is not helping anyone solve the Collatz conjecture because the Collatz conjecture itself deals with an optimization problem. It's not really an optimization problem. It's like more or less a conjecture which says that every single value goes to 1, right? So what an MID does, it returns the maximum value of a sequence of numbers. So say in theory, if you have a recursive relation, you generate a sequence. For an example, of Fibonacci numbers, not really a Fibonacci-esque, but more like something that is not monotonic in sense. So what this MID will do, it will just give you the maximum sequence. But what the approach can at most help you in understanding is that if a sequence is in general not well behaved, like binomial MIDs are well behaved, they just go to 0 if composed with each other. But if some sequence is not well behaved, it is in by just looking at it, it's chaotic in nature. You can, in theory, apply this MID, and under certain regularity conditions, you can compose these over and over again to see whether the chaos like goes away, and you can see a more clear picture, a more deterministic picture in the sense. But yeah, you can't really solve well a very difficult conjecture, I would say, through this method. Okay, so the point is that this is mostly, as I said at the very beginning, a hobby project and a recreational math project. So, what recreational math projects are mostly like, they do not have to blend into some professional math stuff that is going on currently. But at the same time, they can be definitely non-trivial. As you see, that one of the problems that is still left to be resolved. So that might be a bit difficult for me and for someone else out there as well. What I can ask you to read is, see, in most of these cases, it's generally the analysis of binomial functions, but generally learning about Diophantine equations in general from a lot of recreational mathematics is nice. So there are many good books on Diophantine. I don't remember one right now, but Martin Gardner's books are really nice. So he covers, yeah. So like I was doing, I think even Shine is in the meet. So he also knows that we were doing another project just recently, and we figured out a book called Mathematical Plums, and it relates a lot of recreational math problems together. Like one of those problems that you hear about Josephus's problem and so on, which are very nice, very nice riddles and so on. So you could have a look at these, and mostly what you would need to like go on, especially solve the problem that I still cannot resolve. So the kind of tools that you need could be very varied, but it's mostly combinatorics and a bit of number theory. That's what you would need. Yeah. Nice meeting with you. Thank you.